Okay, so I've been getting, just to start, I've just been getting some questions about the homework. I don't know, did any of you try to get together with Finley? I put an announcement up of when his office hours were.
I did, and he helped a lot.
Yeah, he's good. So I just wanted to read this because I just got an email. So I don't know. Does anyone have a question on this?
The second one was just a little confusing with the P1, P2s, and then the Q that appears later on. I guess I was a little confused by that.
Well, it's a little bit like programming. P1, P2, P's and Q's are variables. Coming from the set P, I should have maybe said P, comma P1, comma P2, comma Q in P, the set of all people living and dead. I thought I might get some arguments about, or some questions about Adam and Eve. What about Adam and Eve? I don't know. I mean, if there were such people, then maybe you might say they shared the same father, but they just didn't have a mother.
So I have a question.
Yeah.
Okay, so what is the relation R supposed to be? Because I thought it was like that someone shared a set of parents, but I think I misread it.
Yeah, no. It's that P1 and P2 have a parent in common.
Okay.
Yeah.
I was thinking it was like, sorry, I think I misspoke. I was thinking it was someone's mom and dad, if you will.
No.
So like
P1, P1 and
yeah,
P2 are siblings that share a parent. So you could have a sibling that you only share a father with. You could have a sibling that you only share your mother with. You could have a sibling that you share a mother and a father with.
Yeah, that's what my proof is about, which is completely wrong. But
well, no, but
I think my other
P1. I have a sister named Kim. I don't know. Leave it to my parents, Jim and Kim. So we are in this relation. Yeah. We both share two parents. So actually, this P. There's two P's I could substitute in to make this relationship true for us. And it's also true that my sister, so it's symmetric. It's also true that my sister is a sibling of me, and then I, and vice versa. So this is symmetric. It is reflexive, and transitive it's not, because it's possible that, you share a relationship with someone that shares a relationship with one parent of yours, and then they may share a relationship of being a sibling with someone that has no parents of yours. So it's not transitive. But it's in a way, so, I find it's kind of, in a way, it's a little bit interesting to me, because we often, you often get the complaint that, oh, they're not, it would be much better to have a lot more examples of real world examples. And it seems like this example is the most confusing. I think some people wanted me to write this relation flipping the order, but it doesn't matter. Like in the parent relation. Parent relation is true when P, so the first element is the parent. Some people found that confusing. They wanted P1P and P2P in here. But it doesn't matter. I told you that P in Q, parent PQ, means that P is the parent of Q. So anyway, I don't know. Does anyone have any other questions, or am I beating a dead horse now?
So in the relation, like where it's P comma P1, is P the Q in the parent function?
Well, that would
Because
no.
I understood it as a
Because
pair
this
was a child and a parent.
no, the pair is a parent and a child. That's what it says. Parent PQ is true when P is the parent of Q. So parent P1 means.
So what I'm saying is I thought P1, P2 was a set of parent and child.
But they're not.
Children.
It just doesn't say that. They're siblings. They're not parent and child. I don't know. How about me? I don't know. Let's see. Maybe I can. So I mean, we could build a little part of this relation. I'm not sure. I mean, maybe you're missing that this exists part here, right? This part here says, well, I can't even highlight it because it's, I don't know, this math, the ability to write a formula is kind of limited. But this says, if you see my cursor, there exists a P where P is a person, either living or dead, such that P is the parent of P1 and P is the parent of P2. Then P1 and P2 are in the relation. So the things that are in R are the pairs of people who have a parent in common. Now, if we restricted this to like be the pairs of people who have two parents in common, then the relationship would be transitive. So I guess if I said, what if I write sibling is equal to, are the P's and Q's are problems? I don't know, X and Y, such that there exists a Z, and I can say Z is in the set of persons. So like if you found this notation, exists a P colon P, exists a little p colon big P, maybe this would help. And Z X is the child of Z, and Y is the child of Z. Maybe I should have called it child, but it doesn't actually matter. But all right, so and Y is the child of Z. All right, does that seem better?
That makes 10 times more sense to me personally.
I can't understand though when I say parent P comma Q means P is the parent of Q. I cannot, whoops, Q. That's
Who's
what
the child?
that's what this says right here.
Yeah.
And so I could translate this using that more mathematical notation to say P, maybe I should make this an ampersand because I don't know, that attempt to make a wedge is a little bit unreadable. Let's say like this.
So I think my issue came from seeing parent and parents, and I think what makes the above clearer is it's child and child, if you will.
Yeah, but you still have the same parent, Z.
I know, but what I'm saying is I misread it, and I thought I saw
Okay.
parent and parent, so I thought there was one child and two parents. And now that she's like you've explained it, and I get it, but
Uh-huh.
like
Okay.
before you explained it, I read it as parent and parent, meaning there was one child.
Okay.
But I don't know.
That was exactly how I understood it as well.
Mm-hmm.
And that's where
But
I thought that P and Q were switched. I get that they're not. It makes sense that they're not, but
yeah.
that's it.
Okay. But I mean, it's just a, you know, it's a misreading. I think the information in the problem is all there. Because I defined parent to mean P is the parent of Q. So this means they have P1 and P2 have a shared parent. Now, if you could flip the meaning around, if you found it, you know, but I didn't write it that way. So if I'd written it that way, then the parent would be the second position. But maybe I should have written it as child for more readability. But in any case, those are misunderstandings, so I think of what the problem says. But maybe the lesson is that, you know, these things are a little bit tricky. Okay. Any questions?
I have a question about number 3,
Mm-hmm.
the A arrow B, the function one.
Yeah.
So do you want us to like, I guess I'm not sure what you're asking for. Are we supposed to make a function that relates A to B? Or
You had to do that up here in problem 1. You had
yeah,
to write,
problem 1, number 3.
right. And then this is a generalization saying, look, if the size of A, if there's J elements in the set A, and there's K elements in the set B, how many functions are there? What's the size of the set A arrow B?
Okay. That one I kind of get more, but question 1, number 3 is the one I'm confused about. Are we supposed to be
Oh,
writing
1,
like
3. Yeah, you're
like there's
supposed,
no function?
I'm sorry. Yeah, I thought you said 3. Yeah, you're supposed to write down,
Oh,
you know, something that looks like this, like, you know, so for example, A is 1, 2. And so there's 1 gets mapped to A, and another possibility is that 2 gets mapped to A, for example. So that is in A arrow B, right? But there are a lot of other things in A arrow B, like, you know, 1 comma A comma 2 comma B. That's also, whoops, that's also in A. And so in the end, A arrow B is, whoops, arrow B is a set. And one of the things that's in it is this. And another thing that's in it is this. And there's a lot of other things in there. Right? Does that make sense?
I guess I still don't completely understand. Could you maybe, I don't know if this is allowed, but could you maybe do an example with the different pair sets?
There's an example of it on page 24 of the text.
Okay, I'll take a look at that then.
Let's see. Oh, right. That's a good example. It shows you everything. I mean, you could do a smaller set. I mean, you know, in some ways, like, it's disappointing that most of you have come through 3015 and, you know, there's quite a lot of confusion about functions still. But also 2300 covers this material. And so I feel like somehow we're not really teaching it right. Now, you may have never seen it as this, you know, explicit enumeration of the set of pairs before, but all right. Well, and if anyone else has a question, speak now or forever hold your peace. Well, of course, you know, you can ask me by email or in office hours. No questions? Okay. All right, I'm still trying to figure out the best way to do lectures, but at this point, it could be that this is sort of working. Let's see. Okay, so I wrote kind of two lectures to go with the reading that you've done in the book about first about transition systems, and I'll put these PDFs up on the web page. But now I think I added something. I don't know what this Cami thing is, but boy, oh boy, it wanted to be able to delete everything I have in Google Docs and overwrite all of them and send them all to, you know, anybody, or it was seemed very dangerous. But on the other hand, I'm writing the notes now on my iPad, and then in here I can highlight, and then I can use my, I'm still kind of retarded with with the pen on the Wacom, but I think I can still do some things. Why is it not hooked up now all of a sudden? Oh, there we go. Okay. Okay. So anyway, this is going to be a discussion of the definition of transition systems. And this is from section 3.4 of the book. So let me see, can I? Looks like I can only do a text highlighter. Oh, a box highlighter. Okay, that's fine. So a transition system is a kind of a directed graph, and I kind of assume you probably saw this in 3020 or 2030. I mean, if you haven't seen this kind of presentation of a graph before, raise your hand. It's anonymous. I won't look who you are. I think almost everyone should have, but maybe you haven't. You know, I don't know. It always starts off, oh, a graph is a set of pairs G equals V comma E. And V is the set of vertices. So those, like in this, here's going to be an example down here of a directed graph. And then E is the set of edges. And E is a subset of V cross V. And so when you're doing a directed graph, usually you think of the edges going from the first point to the second. If you're doing an undirected graph, you may just say, okay, there's an edge between this point and that point, which means there's also an edge between the second point and the first point, because there's no direction indicated by edges. It's just a connection that goes both ways. But for transition systems, we're going to be directed graphs. So here's an example of what, a graph could look like. It has 4 vertices labeled A, B, C, and D, and I've drawn them down here. And then if I drew the arrows on here to indicate where the edges go, and this is a looping edge that goes from C to C, I can write down the edges and say, okay, in the set E of edges, there's one of the pairs is AD. Oh, I'm sorry, that should be there is an AD. And then there's an AB. I might have swapped those two to make it a little bit more readable so that they're in what's called lexicographic increasing order, so that they would be in kind of like dictionary order increasing. B comes before D, so it would have made more sense to put that there. But anyway, I've got an edge going here and I've got an edge going there, and BC says there's an edge going from B to C, and CC says there's an edge that loops, that starts at C and goes back to C, and DA says that there's an edge that goes from D to A. So, this graph has no meaning to me except that it's an example of a directed graph. Any questions on representing graphs by these two sets? Okay. So a transition system is just a specific, it's kind of, they use the structure of a directed graph to represent a transition system. The vertices are configurations. What if I go a little bit bigger? The vertices are called configurations. And for the purpose of modeling the semantics of programming languages, those are going to be snapshots of the state of the system being modeled. And so it's going to depend on the kinds of things that we're interested in. But when we come to modeling imperative programming languages, the configuration is going to include like maybe the program to be evaluated together with the memory, the current state of memory. And then if we added, named variables to our programming language, we might need a map that tells us this variable refers to this memory location. So what a configuration is determined by kind of like what the structure is and how complicated a structure we need to interpret the meaning of that thing. But in general, they're snapshots of the state of the system that's being modeled. And we don't call them V anymore, vertices, they're gamma. He uses gamma as the, and not just him. I mean, everyone uses gamma. Gamma is the kind of notation used for the set of configurations. And then individual states or individual configurations are labeled by lowercase gammas. Gamma, gamma 1, gamma 2, gamma prime. Now, if we go back here, you can see that E, this thing, is a subset of V cross V. So E is a relation on edges. And so, or I'm sorry, on vertices. So the edges are a relation on vertices. So the edge relation E in this case is labeled by arrow. And you know, this can be like a little bit confusing. This mathematically, this little bit of text here makes perfect sense. It says that gamma comma gamma prime is in arrow. And you might go like, what? It's in arrow. Well, it's in arrow when you think of arrow as a relation that has a first element, a relation, a binary relation on configurations where the first element is a configuration and the second element is a configuration. So usually instead of writing this like this, we would write it like this. And it reads better like gamma, and then you can sort of think of the arrow as the arrow is called the transition relation. So this sort of says gamma transitions to gamma prime. That's a possible transformation that can occur. And so gamma is a subset of, I'm sorry, arrow is a subset of gamma cross gamma. And remember, gamma is the set of all the possible configurations that you're interested in. Now, we're going to have a third element in the representation of a transition system, which is the set of terminal configurations. And these are labeled T, and T is just some subset of gamma that are, you know, selected out as the terminal configurations. Now, so then we get the definition 3.2. A transition system is a triple, capital gamma, arrow, and T, where gamma is a set of configurations, arrow is a relation on gamma cross gamma, that's the transition relation, and T is a subset of gamma is the set of terminal configurations. Now, I don't know, this thing does not see, will this allow me to draw? I don't know, let's see. No, I don't, oh God. Start a free trial, no. Okay, let's see. So, I mean, the next remark, let me just see if I can sort of, I don't know. Okay, the next remark is that you know, if you start thinking about this, you might go like, well, wait a minute, kind of the intention of T is that you can't get out of T. But if I had like, suppose I had something that went like, you know, like I've got like an A and I've got an arrow to B and I've got an arrow to C. What would it mean to put B in as a terminal in the set T? I don't know. It's kind of an odd thing. because T isn't really terminal in the sense that we want. If you were in state B, you could go to state C. So the point is, I guess, is that it feels like there's a lot of things missing from this definition. So there's no, so if you define the domain of a relation to just be all the first, you just, like if you're thinking in Haskell, you could say, oh, map first over the set list of pairs. If you represented a relation in Haskell as a list of pairs, you could map first over them, and that would be the domain. Those are the points in the relation that get mapped somewhere. And so if you take the domain of the relation and then you intersect it with T, you probably should get back the empty set. That would mean that there's no way when you're in a configuration T, there's no entry in arrow that says, oh yeah, if you're in state B, you can go to C. There should be no entry like that. So there may be some kinds of kind of consistency constraints on these systems, but Huttel doesn't really worry about that because he's never going to define one that has that problem. Does anybody have a question? So I mean, the point is by the definition of transition system, there's going to be a lot of things that are triples that have those three properties, that have those three parts that are not really going to be sensible transition systems. So in practice, what he does for gamma is gamma is a set of is defined as formed. I'm saying here formed as a union of some set of kind of like real configurations, which are the configurations that characterize the state, an intermediate state of computation, and a set of values which don't have any reduction semantics. They're never in the domain of arrow. And it turns out that it's often the case that the set of configurations and the arrow relation will be infinite sets. So once you have an infinite thing, we need to have some finite way to write it down. And excuse me. And the way that we're going to do that is we're going to define an inductively defined relation that is that's keyed off of, it gets keyed off the structure of the abstract syntax tree. So you look at the abstract syntax tree and you find the root of that syntax tree, and there'll be a rule for each of the possible constructs that can be used in the abstract syntax tree. And okay, so that's kind of like the abstract description of transition relations. So does anyone have a question about that? How many people have seen like finite state machines before? or some kind of state machine. Raise your hand. I mean, in your participants menu. Okay, it looks like, I don't know. It's hard for me to tell. It just shows me numbers, first of all. And I can't tell if I'm supposed to add them up or, it looks like 9 and then 10. So that's 20, about 30, 40, 35 people raised their hands. Okay, so almost everyone has seen a state machine before. All right, let me try to open the other notes. Let's see, is this the same? That's the same. Let's see, how do I get to it now? I want to go to my Google Drive. Okay. Okay, so here's the second one, the second part. And so this is the operational semantics for arithmetic expressions. And so if you look at the grammar, I want to open with that, whatever that is, annotate with Cami. I don't know. This is not really that great, but okay. Okay. So, now we're looking at the using these transition systems to describe a transition system. And this is the big step semantics. So he's defining a different shaped arrow here to represent the big step semantics. So anyway, if we look at this, the grammar for arithmetic expressions looks like this, except we're missing one thing. So an arithmetic expression is either a numeral, and remember that's like some representation, like a sequence of digits 0 through 9 to represent a number, or it's a syntax tree of the form A1, where is a syntax tree, A2 is a separate syntax tree, and plus is at the top. I don't know. I'm sorry if my drawing is so bad, but it looks something like this. I've got a plus, and then the left branch looks like this, and I don't know. That's an A1, and the right branch looks like this, and that's an A2. Can I write outside? No. So this thing here is describing a syntax tree that looks like this, right? You've got A1 as the top level constructor, and to the left, I'm drawing this kind of mangled triangle here, trying to express the point that that's a syntax tree, and A2 is a separate syntax tree, and they're connected by this plus in the middle. Now, one thing I've done here is to, oh, where's the eraser? One thing I've done here is to try to make these guys in the syntax look funny. Like this plus is like, you know, a bold plus. And this times is like, you know, this flowery, starry times. And minus is a little bit bolder than you might normally just write it. And we don't have any variables. So then he describes the big step semantics for expressions of this form. And they're pretty boring because you don't have variables. But he says, okay, look, gamma, our configurations are going to be the actual syntactic elements that are in A, the A expressions, union together with the integers. So, you know, he can do this wacky move because we're working in set theory and sets are untyped. And so you can dump whatever you want into it, but you should think of this as being the set of all, there's an infinite number of them, of A expressions. It's every possible A expression described by this grammar up here. And Z is the set of integers. So that's an infinite, I mean, just with Z, we got an infinite number of configurations, and then we add in another infinite set. And those two things, though, are the possible configurations. So remember, we need this arrow thing to be a subset of gamma cross gamma. But gamma is the union of those things. So A is a subset of gamma. So that means that A, and Z is a subset of gamma. So that means A cross Z is a subset of gamma cross gamma. So arrow is something of the right form. It's a set of pairs where the first element, and we're going to restrict it. The first element is an A expression, and the second element is the integer that that A expression evaluates to. And then the terminal expressions are just going to be Z. And the reason that we're not going to run into the problem I mentioned before with the like A, B, C, where they, you know, is that the Z's, the element, the integers, the elements of Z are not going to have any edges from them whatsoever. Okay, so this is the form that a rule takes describing. And what are these rules describing? These rules, well, they can be, you can think of them as describing two things in a way, but it's a describing a recursively or inductive relation. It's a relation that is defined so that says that in this case, for example, if you want to evaluate an A expression where plus is the principal connective, in other words, you have, I don't know, I'm still having trouble drawing, but if you have something that looks like, come on, where you have one of those trees plus, and on the left side you got an A1, and on the right side you got an A2. And this whole thing here is, you know, written as A1 plus A2 with that bold plus. So this here is what the syntax tree looks like for this thing. That's one of the things that's in gamma in the set of configurations. think of it as a bag of trees, but also you've dumped in all the integers. And so we want to be able to say, okay, so A1 plus A2, and he's doing the big step here. So I hope I can do this, is that he uses a kind of a double arrow. Loading what? This is actually like, these are double arrows in the big step semantics. So he's got A1 plus A2 evaluates to V in one step. The idea is that this evaluates in one step if A1 evaluates in one step to V1 and A2 evaluates to V2 in one step. Now, we don't know what A1 and A2 are. The rules are schematic in this kind of the grammatical structure, but we can do an example, and you could see that when you actually write down any sentence that's in the grammar, it's going to look something like this. So you're never going to have these abstract things, A1, A2, and V, but they're placeholders for things where A1 is a placeholder for any A expression, and A2 is a placeholder for any A expression, and V is a placeholder for any int. So how do you evaluate this? Well, you evaluate the left subtree to V1, you evaluate the right subtree to V2, you add them together. Now this addition here is that's real addition in the mathematical notation. These are integers. So this is integer addition. I take V1 and I add it to V2 using integer addition, and I get back the value V. This symbol here is different from that symbol there. And he does have that in the book, but you have to look awfully close to see it. I mean, you got to really look and go like, oh my God, they are slightly different to see that. But if you were working in a kind of a typed language, you'd see like, on top of page 33, the rules, it's pretty clear. So in what way is this specifying how these things go to one another, or what the big step relation is these should have all been double arrows. What does this rule say? It says that, whoops, that's a double R. It says that this pair, this syntactic object, so like this is kind of a weird thing, right? We've got a tree paired with an int, and those two things are in this double arrow relation if and only if A1 evaluates to V1 is in the double arrow relation, and up here, A2 evaluates to V2 is in the double arrow relation, and V is equal to V1 plus V2, where that plus is different from this one. That's real plus. This is just a symbol, you can think of it as a character for plus, whereas this means do the real integer addition. So somebody, I mean, maybe it's all perfectly clear, or you think it's perfectly clear. No question. Come on. All right. If there's no questions, I get to tell you a little story. I took the first like university level math class that I really took was abstract algebra. And the guy that taught the class, and so in abstract algebra, you study things like semigroups and groups and rings and fields. But the guy that taught the class used something called the Moore method to teach the class. And the Moore method is this mathematician at University of Texas invented this method of teaching math. And what you do is there's no textbook, and the teacher will come into the class and write something on the board, and then he'll stand back and just say, okay, how do we proceed? And I learned from this guy how to do proofs, and he would sit up there against the blackboard, and he could just stand there for like 5 minutes. And 5 minutes of silence in a class. Now, this was a very small class. It was at a little tiny college, and I don't know, there were only about, I think there were 5 students that dared to take abstract algebra. And one of them was a musician, and I don't know. I was mostly trained in art at that time, but abstract algebra is very cool because you have the permutation of rotations and everything. He would just stand there until somebody did something. I think he probably could have stood there through the whole class. Maybe he couldn't. I think the original guy, Moore's method, Moore might have been able to. So I could learn to just wait until somebody asks a question. But it's really hard to do. I don't know. I don't really know how to do it very well. So no questions. Okay. There's a lot going on here, even though you may not think there's a lot going on to it, right? What's partially what's happening is that, you have enough training that you can pretty much read these rules and understand what they're saying. And so then you just go like, well, okay, I got it. But there's a lot of these rules are describing the relation, this arrow relation. And so you're kind of here. This is a little bit weird because it's recursive in a way, or it's inductively defining them, because here I'm saying, look, this pair is in the arrow relation if this pair is in the arrow relation. So I'm defining the arrow relation, this bold arrow relation, by using the bold arrow relation on the right-hand side of the definition. And so you could rewrite all of these rules out for each of the rules. So here's all the rules. I mean, you can turn off your video and speak anonymously. I can't even tell who's speaking, actually. All right. I dare someone to ask a question. No.
Sorry, Caldwell, I don't know.
I'm trying to come up with one.
All right. Okay. Well, anyway, so here's the rule that, whoa, I didn't mean to do that. I wanted to highlight. That's the rule we just saw up above. And so he calls this plus. Well, I want to be drawing with a markup. There we go. So he calls this rule plus BSS for big step semantics. And that's what we just saw. And obviously there's a rule for minus. Now that should be a different minus than this minus, because this one we're doing real arithmetic. And this is just a syntactic object that is at the root of the syntax tree for this expression. You take this left sub-expression, you evaluate to V1. You take the right sub-expression from that tree, you evaluate to V2, and then you subtract them and you get back the answer V. Multiplication. Now notice he uses in the book, he uses a dot for mathematical multiplication and kind of like, you know, an asterisk or star for the syntactic form of multiplication. So this one actually separates out kind of better. And again, pardon me, you evaluate A1 to V1 and you evaluate A2 to V2, and then you multiply those two together to get the answer V. Now this parent one is just says, oh, if I have an expression that has parentheses around it, how do I figure out what that evaluates to? Well, just remove the parentheses and see that one and figure out what that evaluates to. And then he has this rule that, I mean, you know, I'm pretty accurate here on the translation from the book of what it looks like. N evaluates to, oh, I should have put over here though, V. Oh, come on. And evaluates, oh, it's on yellow, block. And evaluates to V if, and I don't know, he uses kind of fancy notation to mean translate the numeral N into its integer value V. So whenever you see this funny thing here, that means translate the numeral, and remember a numeral you can think of, like one way to think of numerals is it's a sequence of digits 0 to 9 that starts with the 0 if and only if it's the whole sequence is 0. Now, one of the things that's going on here is that these rules are compositional. So you're figuring out, for example, the meaning of this more complex term by decomposing it and saying, okay, get the left subterm A1 and get the right subterm A2 and figure out the meaning of those, and then combine them in a way to figure out the meaning for the composition of those two things. And so that's a property that, like, oh, I can't think of really semantics where you don't have that property. I mean, you know, I guess you could have maybe like a every element could be paired with a little comment. So you could have a transition relation that pairs every expression from some language with a comment, and then they evaluate to integers, but the comment plays no role whatsoever. You just throw them away. So that might be kind of, you know, but you'd still need to do compositional semantics on the part that you are using. So the structural operational semantics for the,
Excuse me?
yes.
Why is there no rule for division?
Well, we don't need a rule. I mean, you could add a rule for division, but when we get to the full language, like you could write a division using a while. So you could write a program once we have statements and we have Booleans, you could write a program to compute, you know, A divides B.
isn't it because like in the reading it said something about like the star like doesn't represent multiplication, but it represents like some category that I understood to mean both multiplication and division and just that sort of thing.
Well, it can't really because he only has integers. So I mean, if we could say like, you know, if we had um, rational numbers, we could take any number and put, you know, 1 over that number. You know, we could express division then by a1 divided by a2. But can somebody mute themselves? I don't know. I'm hearing like some back talk. Thank you. Did I lose everybody? No. Raise your hand if you okay. So no, what they're saying, what he's saying there is what I've been saying kind of like over and over again is that this star here is a constructor for making A expressions. And this over here is multiplication. The dot is multiplication. Now, unfortunately, he kind of like overloads. But if you look in the book very closely, the plus that he uses in the syntax is like a little bit bolder, and maybe it's in like typewriter font instead of being in like regular font. You see that on page 33 if you have your book. Right on the top, you can see the plus sign is different here than the plus sign is different there. So that's what he's saying there is he's saying this is real. The one over here on the right is the real plus that you know. This one is something that's just a constructor. I think I can make it more clear maybe by going and looking like, I don't know, let's see. The first problem is I got to find the file. Let's see. So I think last time, did we look at some code like this last time? Where this is a representation. Whoops, let me move this out of the way. If we look at the syntax here, note that, you know, we excluded variables. And so this one has a constructor for variable, but this is a data type in Haskell that defines the tree, this language, the abstract syntax tree of this trees of this language. Now, well, sorry, didn't mean to make that go away. In this version over here, I could have made this more faithful by saying that the constructor applied to a list of this thing here could be like, you know, a list of digits from 0 through 9 or something, right? But who cares? We're just going to, that translation that's in that funny n function down here is not really that interesting. So I'm just going to put an integer in there and wrap it up with a constructor num. So num applied to an int gives me back an A expression. Now, plus, here you can see the constructor name is totally different. This plus in this notation is kind of like trying to to be more what you would write down. This is a program. We don't care. I mean, you could, if you remember, you could write this as an infix like that if you wanted to. So it's an A expression plus an A expression. Mult, see, mult, and then down here in the actual implementation of these big step semantics, like if we go look at this rule here, is characterized here by this bit of code. So we're saying big step, and I say A prime here because the big step A is the one that has variables in it. So this is the one that leaves out the variables. So big step A prime says if I have a syntactic object that looks like a syntax tree, which has root is plus, that's what we're saying here with this plus over here, and whose left subtree is A1 and whose right subtree is A2, that evaluates under the big step semantics to V, as long as A1 evaluates to V1 and A2 evaluates V2. And notice that here I'm using the real plus from Haskell, the plus that works on integers. Whereas this is just a constructor for this syntactic thing. Does that make sense? Now, why not have division? Well, there's a few reasons not to have division. Perhaps the main one is that every time we want to prove something about this language, we have to consider every possible constructor in the language. And so if you put these in, you pretty much, in fact, I don't even think, you don't really need minus here because you could just make a number which is a negative integer if you allowed for numerals for positive and negative numbers. So you could get rid of minus, and then all you need is plus and times. Parentheses are good for organizing things. So whoever asked that question, did that answer your question? There were two questions, really. Why is divides not there? And I think divides is not there mainly because every time you extend it, you have to do more things with these. You have to prove things about all the rules that allow you to construct or to do this evaluation. But what he means by this is not really addition, it means it's the syntactic thing. This here is syntax in our programming language. These here are integers, real integers. They're, God's integers. Like if you're a Platonist about mathematics, there are these things that live out there somewhere in the universe. Like what is the number 1? Now, famous mathematician Kronecker, who is more inclined to be constructive, would say, God gave us the natural numbers. The rest is the invention of man. So integers he's put into that category, but it's pretty easy to characterize integers once you have the natural numbers. Okay, so let's look at an example. If there's no more questions. Let's look at
I have a question.
Oh, good. Okay, go on.
How do the operators have precedence? Does this, or is that left up to the parser? So like if we type out the expression at the bottom of that page, how do we know to do?
Well, I mean, he sort of says on, I think it's on page 34. I mean, somewhere he basically says, we just adopt the standard. If you don't have parentheses, use the standard precedences. Oh, no, it's on page
Yeah,
30.
But where in the programming does it say that, or does it not?
That's an interesting thing. I mean, the parser, like you said, like generating, the parser takes an input of a string and generates the abstract syntax tree. And the abstract syntax tree is explicit about the structure. It is a tree already. And so, I think I talked before about issues of precedence a little bit where like, you'd say like, oh, you could have, oh God. You could have like, at the root of the tree, you might have times, and on the left side, you have plus, and you have like whatever, X, or let's make it an A and a B. And then over on this side, you might have a 2. But from the string that represents that tree, you could also have this as A plus B2, right? Because this would be like I'm sorry. This is A plus B times 2. And so this one here, I need an eraser. It's still the operators have to stay in the same order. Where did the eraser go? I'm sorry, this is really painful. So this stays the same. Plus is here. And times is here. So these are two possible interpretations of this sequence of characters, depending on what the precedence, how you interpret the precedence of these operators. And so this would be the normal one, but we don't care about precedence for us because we don't have to worry about it. We're working with abstract syntax trees. Once the parser parses, this string, say this is a string coming in, the parser is either going to generate this tree or it's going to generate that tree. And what we're going to get is a tree, an abstract syntax tree. So it eliminates that from consideration. In compilers, you have to worry about that a lot. I mean, even last semester, and if you took 3015 last semester, we looked at that problem in parsing. If you want to have like left associative parsing with grammar parsing from left to right is kind of a pain. And answer your question?
Yeah, it did.
Okay, so let's look at this. I kind of wish I could put the 2 pages side by side because I didn't label the rules here. Well, maybe I can try with this thing. So this rule here is the plus rule. The plus BSS rule. And so A1 in that case is the numeral, and he's writing, when he writes this down, he writes underscore under a number to mean it's a numeral. So in this case, this is the A1, this is A2, and this is V. And so how do I build this tree? Well, I look at over here and I say, okay, the rule for plus tells me take A1 and go up and figure out what the value of that is, and take A2 and go up and figure out what the value of that is. and then add those two values together to compute V. So when I'm building this tree, I don't know that this is going to be -3. I have to wait and see. So I recursively call BSS on this one, and it goes over here, and it says, okay, 1 plus 2. Oh, wait, though, it's got parentheses around it. So the first thing I have to do is apply this rule, paren BSS, to get rid of the parentheses. And so this rule over here is going from here to here is paren. Ah! This is going to drive me nuts. And then over on the, oh, he calls it paren T. I don't know why. Parent, okay. And then this rule is the same. Take this and go to there, erase the parentheses by the paren rule, or the parent rule. Parent BSS. I'm not writing the BSSs. Okay. And so then I'm here. And this one, I apply again the plus rule to go from here to here. And so this is the plus rule again. And this rule from here to here is the minus rule. And so for the plus rule, it says going up and evaluate underscore A, and underscore A evaluates to 1. And go out, take this is the A2, evaluate A2. A2 is the numeral consisting of just 2. That evaluates to the integer A2. And so to get the answer down here, what do? I add 1 and 2 together to get 3. But over here, I do what? I subtract 3. I subtract 4 from 3 to get -1 over here when I'm coming back down. And so now I have a -1, so I know that's the meaning of the parenthesized version. And then I know that I've got a -1, and I multiply that times 3, and so I get a -3 down here. So you're kind of going up and coming back down, and that's what can be reflected in a nice way in the code by recursion and getting the answer to the recursive call. So for like the rule for plus, if I got this in here, the rule for plus says, okay, evaluate the meaning of A1. And then in this case, so let's try this. I don't know, what time is it though? Are we over? My problem is my, when I share my screen, I can't see the time. Can somebody tell me the time?
2:41.
Okay. Oh, so I'm well over. Sorry. Okay. So I'll probably give you this code, and I will put up a homework and ask you to maybe, I don't know. The next part was you can also see these rules as describing. This is a derivation tree. This is a derivation that shows that this syntactic A expression evaluates to this integer. This shows that this pair of this expression and this integer are in the arrow relation, and how you use the rules to derive it. And so it's a kind of a derivation that in fact this pair is in that relation. And the code includes like an actual data type for representing derivations like this where they're labeled, where the rules are labeled. So we'll talk about that more next time. I apologize. I need to get a different clock or something. Any final questions? feel free to leave, but if you have a question, I'm happy to answer it. Okay. Looks like most everyone's gone. Hey, Tim, do you have a question? No.
No.
Okay. All right. See you.